So we're going to continue our discussion of this new vector math operation called the cross product. Whenever you are crossing two vectors, you're taking two vectors and generating a new vector. That's the result of the cross product. And that new vector is going to be perpendicular to both of the vectors that were in the cross product. And this is a brand new vector operation. It is very different than the dot product, adding, subtracting. Please don't confuse the dot product and the cross product, because in regular scalar math, the x, the dot, all of that just means multiplication. In vector math, when we're dealing with vectors, they have completely different meanings. So now we're going to talk about the cross product in a different way. We talked about the graphical method already. Now we're going to talk about the component form method. So if you're working in a Cartesian coordinate system, you've already learned how to get the directions of the Cartesian unit vectors using something called the right-hand rule. The reason that this right-hand rule is true is that the Cartesian coordinate system is actually defined by a cross product. You already know that you would put x hat on your pointer finger, y on your middle, and z would be your thumb. So the Cartesian coordinate system is defined by the cross product x cross y equals z. This kind of lines up with what we talked about in the graphical method of how to get the result of a cross product using a right-hand rule. So in the Cartesian coordinate system, like I said, it's actually just a definition of the Cartesian coordinate system, that these vectors are perpendicular to each other. So x hat is perpendicular to y hat, is perpendicular to z hat. All combinations of that, all three of those unit vectors are mutually perpendicular. And they are defined by this cross product here, that x cross y is equal to z. So using our right-hand rule, x is your pointer, y is your middle, z is your thumb. The cross product has some interesting properties to it that actually allow us to move things around within that definition, and we can generate equivalent definitions of the Cartesian coordinate system. Actually, we could write down that z crossed with x is equal to y, and y crossed with z is equal to x. So there are actually three definitions that I will give you for the Cartesian coordinate system. I will give this to you on the exam, that x cross y is z, z cross x is y, and y cross z is x. Those three definitions I'll give you. Any other ones that you might need to know, you'll have to use other properties of the cross product to understand those. We can talk about that now. So let's talk about, let's say we have two vectors that are written in component form, where A is its scalar component times x hat plus its scalar component times y hat plus its scalar component times z hat. So I have my three different scalar components along the various Cartesian coordinate system unit vectors. And B is also written the same way. So if you have your vectors already given to you in component form, and then you're asked to find A crossed with B, you can distribute the cross product just like we did previously when we distributed dot products. It's like foiling out a bunch of terms. You just have to be careful with all of your terms and make sure that you foil correctly. And because the order of the vectors in the cross product matters, you have to be a lot more careful with what is being crossed with what. So I would first write down my two vectors in component form and then write that cross between them. So that, I know it looks like an X, it's a cross. So A crossed with B. Now I'm going to foil or distribute that cross product among all the terms. So I have the first term, that little A sub x, x hat, is being crossed with B sub x, x hat. And then A sub x, x hat is being crossed with B sub y, y hat. You can FOIL this out. You would get 9 different terms, and each of them has a different cross product relationship. So you'll have x crossed with y's, x crossed with z's, y's crossed with x's, y's crossed with y's, y's crossed with z's. It'll take you a while, but you could write down all 9 of those terms. I'm just going to write out the first few of them so we can kind of look at these relationships. So A sub x and B sub x, those are scalars, just numbers. The cross product is happening between x hat and x hat. In the next term, again, A sub x, B sub y, those are just numbers being multiplied together. What you have is x crossed with y. The next thing was x crossed with z. Now notice when I started crossing the next term, when I started doing a sub y, y hat, crossed with each of the terms in the b component form expression. Now I'm crossing y hat with x hat. So notice that this order of the vectors in the cross product, it matters. You'll pick up negative signs, you'll mess up the addition if you don't keep that order as it was written. So be really careful with that. But you could write out all 9 of those terms. Then we're going to use some relationships between the Cartesian unit vectors. We already know 3 of them. I gave them to you on the last slide. But we're going to actually generate all of the needed cross-product relationships using the Cartesian unit vectors. We know what these are because it's defined within the Cartesian coordinate system. And that's what allows us to take this kind of, messy, complicated expression, and it's actually going to simplify a lot. So we need to get definitions for all of these cross products that will form when we FOILed out all of these terms. So write this down, take your notes. We're going to understand and be able to generate all 9 of what the result of all of these cross products are. We already have a few of them. So remember the definition of the Cartesian coordinate system said that x crossed with y is z hat. So that's an easy one. That's just alphabetical order. There was 2 other ones that I gave you. I also told you that y crossed with z is x hat. So that one right there, that's an x hat. I also told you that z crossed with x was y hat. So those 3, I will give you those on your equation sheet. You are responsible for being able to construct the rest of these, the 6 ones that are remaining. And remember, a property of the cross product is that it is anti-commutative. If you invert the order of the 2 vectors in the cross product, you get a negative sign. So if I know that x crossed with y is z, that means that y crossed with x is negative z. So I was able to come up with this one kind of on my own using the property of anti-commutivity. Let's see, we know that y crossed with z is x. That means that z crossed with y is negative x. And then I know z crossed x is y. That means that x crossed z is negative y. So I got those 3 just based on anti-commutivity. The last 3, notice that you have x crossed with x. That's a unit vector being crossed with itself. If you think about the norm of the result of this cross product, the norm of x crossed with x, that would be the norm of the first vector times the norm of the second vector times the sine of the smallest angle between them. Now x is a vector being crossed with itself, so the angle between x and x is the angle 0. The sine of 0 is 0. So any vector crossed with itself is always going to result in a cross product of the 0 vector. So x crossed with x is the 0 vector, y crossed with y is the 0 vector, and z crossed with z is the 0 vector. So I was able to get all 9 of those relationships. 3 of them were given to me, and I was able to get the other 6 just based on properties of the cross product itself. So you definitely want to remember those properties and be able to apply them based on the 3 that I do give you. You should be able to get all 9. But now that we have those relationships, we can use them as we're FOILing out terms, and we can simplify our terms using those definitions. I just want to alert you to a common mistake that students make. Because they're very used to doing dot products, they kind of fall into habits that do not apply when you're doing cross products. Let's say that you're trying to find the cross product between x hat and y hat. It's very common for students to just immediately write down, oh, norm of the first vector, norm of the second vector, sine of the angle between them. And they would see that if they did this, they would say, oh, well, the norm of x hat is the number 1, norm of y hat is the number 1, sine of 90, all of that gives me the number 1. And they would write down that x crossed with y is equal to the number 1. Something is very, very wrong about this. Remember that the cross product generates a new vector that's perpendicular to both of the vectors in the cross product. So to write down that x crossed y is equal to a number doesn't make any sense. because the result of a cross product is a vector. So a vector cannot be equal to a number. So the mistake that you're doing here, if you wrote this down, is what you were finding was actually the norm of the cross product between x and y. And I agree with you, using the graphical method, that the norm of x crossed with y is the norm of x times the norm of y times the sine of 90. So the norm of x crossed with y is the number 1. I do agree with that. That is a true statement. Using the definition of the Cartesian coordinate system, though, or you could use your right-hand rule, that the result of x crossed with y is z hat. So x hat crossed with y hat is equal to z hat. And yes, the norm of z hat is the number 1. That is true. It's just a unit vector. It's kind of trivial to even write that down. Just be really careful that when you're doing cross products, your answers are vectors, not scalars. All right, so let's do an example here together, actually performing a cross product in component form, and then we're going to even check it with the graphical method that we talked about in a previous video. So we have two vectors here, P and R, and there's a new vector called L. This is something called angular momentum. It is equal to the cross product between R and P. So we are going to use the right-hand rule just to kind of check and get the general direction of what L should be. And then we're going to write everything out in component form and see what the final answer actually is. So let's do a right-hand rule right now to actually get the graphical answer to the direction of vector L. So using our assignments, L is the result, so that makes it L your thumb. R is the first vector in the cross product, that's your pointer finger. And P is the second vector in the cross product, that's your middle finger. So right now, if I put my pointer finger down and to the right, my middle finger is going down and to the left, my thumb is going into the board. So based on the right-hand rule, now let's perform this cross product using the component form expressions and distributing the cross product. So vector L is the result of R crossed with P. So the first thing I do is I write down my two vectors, I put them in parentheses, put a cross between them to show that you are doing a cross product. I'm going to move the units off to the side just because it's going to get kind of messy. So I'm just factoring the meters out of that first expression. I'm factoring the kilogram meters per second out of the second expression, which means that the units of my final answer will be kilograms meters squared divided by seconds. And I'm going to put that over there on the right, and then it'll appear in my final answer, but I'm not going to write it every single step of the way. And that's perfectly fine if you want to do that as well. Just don't forget to put it into your final answer. You do run a risk of forgetting if you do it this way. All right, so I have my two expressions. I am now distributing a cross product. So 3x crossed with negative 4x hat. Then I have 3x hat crossed with negative 5y hat. Then I'll have negative 2y hat crossed with negative 4x hat. And then negative 2y hat crossed with negative 5y hat. So that's where I'm going to get these four new terms. I've distributed that cross product among all of the terms, and I've been very careful to maintain the proper order of the vectors in each cross product. Now I'm going to reduce these cross products with the definitions that we just talked about a few slides ago from the Cartesian coordinate system. X crossed with x, that's a vector crossed with itself, so it is automatically the zero vector. X crossed with y, that equals z hat. Y crossed with x, that gives me negative z hat. And y crossed with y, that's another vector crossed with itself, that gives me another zero vector. So simplifying that together, this term is going to die because the zero vector times anything is still the zero vector. I have a negative 15 z hat and a negative 8 z hat. Altogether, I have negative 23. I'm going to bring back my units here. Kilogram meters squared per second, z hat. So there's my final answer. That is a vector. It's in component form. It just has one vector component, and it's in the negative z direction. And what do you know? That actually agrees with our right-hand rule that we did previously. We predicted that L should be pointing into the board. And according to our coordinate system, negative z hat, that points in the opposite direction as z hat, that would be pointing into the board. So we did everything correctly. Our two methods agree with each other. And this is our final answer for vector L. One more thing that I just want to give you, this will come up later on when you get into Physics 1 and Physics 2 especially. There are certain vectors in physics that the way that they came about is in a special way. They're called axial vectors, and they're related to a rotation. So for vectors that cause rotations, these are vectors that, they're special vectors called axial vectors. They're the result of a cross product. Then you can actually describe the direction of rotation using what I call the screw rule for cross products. And it's very simple. They are the result of a vector, or sorry, they're the result of a cross product. So that means that your thumb is already describing their direction. The way that your fingers curl around, that tells you the direction of rotation associated with these vectors. So to give you an example here, we'll talk about these two vectors, this is R and F, and we're going to talk about a vector called torque. Torque describes how something is rotating due to an applied force. So the way that we're pushing on this, imagine this is a wheel, and you kind of give it a push up and to the left. You guys know that this wheel is going to start rotating counterclockwise. So torque is the result of R crossed with F. So doing your right hand rule, put your pointer finger in the direction of R, put your middle finger in the direction of F. My thumb is coming out of the board. So torque, that vector tau, it's coming out of the board. And so if you point your thumb coming out of the board, the way that your fingers curl around, that gives you the direction of rotation. So my fingers are curling around counterclockwise. And so honestly, this is the justification for the phrase righty-tighty, lefty-loosey. It's really just coming from the screw rule for cross products, that all of our things that are have lids on them and stuff like that, screws and various things that you might, turn, they're right-handed. They go with a right-handed coordinate system. It's kind of how our society was built, unless you have like a specific left-handed screw. Then you can actually, the reason that says righty-tighty, lefty-loosey is actually coming from the cross product. And so if you want a lid to come up, point your thumb up, and your fingers curl around in the way that you need to spin to turn the lid. If you want the lid to go down, now your fingers are going clockwise, and so you're actually turning right. So righty-tighty, lefty-loosey, that's where that phrase actually comes from.